Tonight, we're going to dismantle something so ordinary you have almost certainly never questioned it. The idea that some things, at least some things, are still. That a rock on a table is genuinely not moving. That the ground under your feet is at rest. That between the quantum world of vibrating particles and the astronomical world of galaxies speeding through space, there is some middle scale at which things are actually, genuinely, completely motionless. That stillness is a real physical state that exists somewhere in the universe and can in principle be achieved. It cannot. Stillness, in the sense of genuine, complete, absolute absence of motion, does not exist anywhere in the universe at any scale. Not at the scale of atoms, where the uncertainty principle of quantum mechanics mathematically prohibits a particle from having simultaneously definite position and zero momentum. Not at the scale of everyday objects, where even the coldest material object contains atoms vibrating with thermal energy that cannot be extracted to zero. Not at the scale of planets, which orbit their stars while those stars orbit their galaxies, while those galaxies move toward attractors distributed through the cosmic web while the universe expands and carries everything within it outward. Not even in the emptiness of space itself, which is not empty at all, but is permeated by quantum vacuum fluctuations that represent a form of energy and motion inherent to the nature of quantum fields. The picture of the universe as fundamentally in motion, rather than fundamentally at rest with things occasionally disturbed from stillness, is not a metaphor. It is the literal description of what physics has found at every scale it has examined. Motion is not something that happens to things that would otherwise be still. Motion is the default condition of all matter and all energy at every level of description that has ever been successfully tested. The implications of this run deeper than most people appreciate. The fact that you feel stationary right now means not that you are stationary, but that the particular combination of motions you are embedded in, orbital, galactic, cosmic, thermal, quantum, all happen to cancel at the scale of human perception. Your nervous system is a device calibrated to detect differences in acceleration, not absolute motion, and the motions that carry you through the universe are smooth and consistent enough that you feel nothing. This is not stillness. It is an experience of stillness that is produced by being in smooth, unaccelerated motion through a universe that has never contained a single, genuinely motionless thing since the moment it began. By the end of tonight, you will understand exactly why stillness is impossible at every scale and through every mechanism physics has identified, what it would actually require to come close to stillness at specific scales and why even coming close encounters absolute barriers, and what it means for our understanding of a universe that motion is not an occasional perturbation but the fundamental, irreducible, unavoidable condition of everything that exists. If this kind of foundational, precise, physically complete examination of an idea everyone takes for granted is what you come here for, subscribe and leave a like. It helps this channel find people who want the honest answer rather than the comfortable one. No? Let us begin with the closest thing to stillness in everyday experience and show why it is not stillness at all. The story of why nothing is ever still is also a story about what motion means at different scales and why the same physical laws that forbid stillness in a single atom also forbid it in a galaxy cluster. This is not a coincidence. The prohibition on stillness runs from the quantum mechanical to the cosmological through a set of principles, conservation laws, and uncertainty relations and thermodynamic limits that are themselves deeply connected. The universe is not merely one that happens to be full of motion. It is one in which motion is the necessary consequence of its most fundamental laws. There is also a perspective shift worth establishing at the outset. Most of the time, most people think of motion as something that needs a cause, a push, a source of energy. Things are assumed to start still and then be set in motion by something. This is not wrong as a practical observation in certain everyday contexts, but it is wrong as a fundamental description of how the universe works. At every scale where we can look carefully, the question is not why things are moving, but why they appear to slow down or stop in some contexts. And the answer is always that they have not stopped and never will. That what looks like stillness is always motion at a different scale or a different rate than the one being observed. The default is motion, and the apparent exceptions are always just motion in disguise. The most instructive starting point for understanding why nothing is ever still is to examine the experience of stillness as carefully as possible and then trace through exactly what is not still in what appears to be a completely static situation. Consider the simplest case, a stone sitting on a table in a room. Nothing about this situation suggests motion. The stone is not vibrating visibly. The table is not shaking. The room is not moving. The stone has been there for years and shows no tendency to go anywhere. This is the paradigm of stillness in everyday experience, and it is wrong at essentially every level of description. Starting at the largest scale and working down, the room containing the stone is sitting on Earth's surface. Earth rotates on its axis once every approximately 24 hours, which means a point on the equator is moving at about 1,670 kilometers per hour relative to the Earth's axis. At middle latitudes, say the latitude of the continental United States, the surface speed due to Earth's rotation is roughly 1,200 to 1,400 kilometers per hour. The stone is moving at this speed right now, continuously, and has been since it was formed. The stone is not still. Earth is also orbiting the Sun. The average orbital speed of Earth is approximately 29.8 kilometers per second, about 107,000 kilometers per hour. Earth has been making this journey for about 4.6 billion years, completing roughly 4.6 billion orbits, each one covering about 940 million kilometers. The stone participates in every one of these orbits. It has never been still relative to the Sun. The Sun is not still relative to the rest of the Milky Way. The solar system orbits the galactic center at approximately 220 kilometers per second, roughly 792,000 kilometers per hour. The orbit takes about 225 to 250 million years to complete, and the solar system has completed approximately 20 such orbits since it formed. The Milky Way galaxy itself is moving relative to other galaxies in the local group at roughly 600 kilometers per second in the direction of the Virgo cluster and the Great Attractor beyond it. Returning to the smallest scales, the stone is composed of atoms, and those atoms are in continuous thermal motion. At room temperature, roughly 293 Kelvin, the atoms in the stone's crystal lattice are vibrating about their equilibrium positions at speeds of hundreds of meters per second, performing billions of oscillations per second. The higher the temperature, the faster and more energetic this motion. At room temperature, the thermal energy corresponds to motion that is invisible to the naked eye, but is continuous, rapid, and measurable. Even if you could cool the stone to temperatures approaching absolute zero, the atoms would still be moving, vibrating with zero-point energy that quantum mechanics requires even at the theoretical minimum temperature. The stone's electrons are moving. In a conductive material, some electrons move freely through the crystal lattice. In the stone, a non-conductor, electrons are bound to atoms but are in continuous quantum mechanical motion, occupying orbitals that describe probability distributions for their positions, never localized to a specific point, never truly still. Every piece of what appears to be stillness in the everyday world dissolves under examination into a hierarchy of motions, from the rapid quantum vibrations of atoms to the stately cosmic journey of the solar system through the galaxy. The appearance of stillness is an observational artifact of a human perceptual system's sensitivity range, not a physical reality. The history of physics is in part a history of discovering that things previously thought to be still are moving. Before the Earth's rotation was established as a physical fact, the firmament of stars appeared to rotate around a stationary Earth. The recognition that it was Earth rotating, not the stars orbiting, required a conceptual revolution that was resisted for both astronomical and cultural reasons. The daily motion of the sun across the sky, the most regular and dramatic motion in everyday experience, turned out to be the illusion created by Earth's rotation. Similarly, before the Copernican revolution established the heliocentric model, the sun appeared to orbit Earth once per year, and the Earth appeared stationary at the center. The transition from geocentric to heliocentric understanding required accepting that the Earth's apparent stillness was an illusion produced by being on a moving platform. The same lesson has been repeated at every subsequent scale. The The solar system appeared stationary relative to the stars until proper motions were measured and the Sun's galactic orbit was established. The Milky Way appeared stationary until a motion of galaxies was discovered and the local group's motion toward the Great Attractor was measured. At each step, something that appeared still turned out to be moving. The universe has consistently provided this lesson, and the lesson applies not just to larger and larger structures but to smaller and smaller ones as well. The apparently smooth surface of a solid material contains atoms vibrating at hundreds of meters per second. The apparently quiescent space inside an atom contains electrons in quantum states with kinetic energies enormously greater than thermal energies. The layered discovery of motion at every scale is one of the great themes of the scientific project. One of the most profound discoveries in the history of physics was that heat is not a substance but a form of motion. The caloric theory of heat, which proposed that heat was a fluid-like substance that flowed from hot bodies to cold ones, dominated physics until the middle of the 19th century. Its replacement by the kinetic theory of heat, which identified heat with the kinetic energy of randomly moving molecules, was one of the major conceptual revolutions in scientific history and one that transformed the meaning of the word stillness permanently. In the kinetic theory of gases, the temperature of a gas is directly proportional to the average kinetic energy of the molecules composing it. The relationship is precise. The average kinetic energy per molecule is 3/2 times Boltzmann's constant times the absolute temperature. Boltzmann's constant is approximately 1.38 times 10 to the negative 23rd joules per Kelvin. At room temperature, 293 Kelvin, this gives an average kinetic energy of roughly 6 times 10 to the negative 21st joules per molecule, which corresponds to an average speed for nitrogen molecules, the dominant component of air, of about 515 meters per second. This is faster than the speed of sound in air, roughly 343 meters per second, and every breath you take contains molecules moving at these speeds in random directions, constantly colliding with each other and with the surfaces they encounter. The Maxwell-Boltzmann distribution, derived by James Clerk Maxwell in 1860 and extended by Ludwig Boltzmann, describes the full distribution of molecular speeds in a gas at any given temperature. The distribution is not a spike at the average value, but a broad curve with some molecules moving much more slowly and others much more rapidly than the average. The faster tail of the distribution extends to speeds significantly above the average and represents the molecules responsible for evaporation from liquid surfaces, chemical reactions, and other phenomena that require above-average energy. In solids, thermal motion takes the form of vibrations rather than the free translation of gas molecules. The atoms in a crystal lattice are bound to neighbors by chemical bonds, and these bonds act like springs. The atoms oscillate about their equilibrium positions, vibrating at frequencies determined by the strength of the bonds and the masses of the atoms. In typical crystalline solids, these vibration frequencies are in the terahertz range, meaning the atoms complete trillions of oscillations per second. The amplitude of these vibrations increases with temperature and decreases as the material is cooled, but never reaches zero, not even at absolute zero, because of quantum effects. The thermal motion in solids is not perfectly ordered. The vibrations of neighboring atoms are correlated, producing wave-like disturbances called phonons that carry both energy and momentum through the crystal. Phonon scattering is the primary mechanism by which metals and other solids conduct heat. Energy flows from hot regions to cold regions through the propagation of these lattice vibration waves. When you touch a hot surface and feel heat flowing into your hand, what is happening at the microscopic level is that the rapidly vibrating atoms of the surface are colliding with and transferring energy to the atoms in your skin, eventually reaching the nerve endings that register the sensation of warmth. The universality of thermal motion is what makes a universe of complete stillness thermodynamically impossible. As long as any object has a temperature above absolute zero, its constituent atoms are moving. The statement "nothing at finite temperature is still" is not a useful approximation but a rigorous consequence of the kinetic theory of matter and thermodynamics, confirmed by every temperature measurement ever made. The quantitative description of thermal motion produces some numbers worth sitting with. A nitrogen molecule in room temperature air has a root mean square speed, a kind of average that gives a sense of the typical speed in the distribution, of approximately 515 meters per second, about 1,850 kilometers per hour. This is roughly the speed of a rifle bullet. Every nitrogen molecule in the air around you is moving at bullet speed in a random direction, colliding with other molecules about 5 billion times per second, bouncing around in an invisible storm of collisions. The fact that you feel a gentle breeze when the wind blows rather than a stream of bullets is because the storm is isotropic. The bullets come equally from all directions, and their net effect is nothing until a macroscopic pressure difference creates a net flow. The pressure you measure when you pump up a bicycle tire is the cumulative force of trillions of molecular impacts per second on the inner surface of the tire. Normal atmospheric pressure, roughly 101,325 pascals at sea level, corresponds to about 3 times 10 to the 23rd molecular impacts per square meter per second on any surface exposed to air. When you inflate a tire, you are compressing more molecules into the same volume, increasing the number of impacts per second and therefore the pressure. The tire is not pushed outward by anything mystical. It is pushed outward by the continuous kinetic energy of the nitrogen and oxygen molecules inside it, never resting, always moving, always imparting tiny impulses to every surface they strike. The implications of thermal motion for chemistry are equally profound. Chemical reactions occur when molecules collide with sufficient energy to overcome the activation energy barrier between reactant and product states. The Maxwell-Boltzmann distribution of molecular speeds means that even at room temperature, some fraction of molecules have speeds and therefore kinetic energies far above the average. These high-energy molecules are the ones that drive chemical reactions at ordinary temperatures. A reaction that requires a specific minimum collision energy will proceed at a rate that depends on what fraction of molecules in the thermal distribution have enough energy to meet that threshold. Even if thermal motion could somehow be eliminated by cooling a system to absolute zero, quantum mechanics independently and absolutely forbids stillness at the atomic and subatomic level. The principle that enforces this is the Heisenberg uncertainty principle, discovered by Werner Heisenberg in 1927. And it is not a statement about measurement limitations or about the clumsiness of experimental equipment. It is a fundamental statement about the nature of physical reality, a mathematical theorem within quantum mechanics that applies regardless of how sophisticated or perfect any measurement technique might be. The uncertainty principle, in its most commonly stated form, says that the product of the uncertainty in a particle's position and the uncertainty in its momentum cannot be less than the reduced Planck constant divided by 2. Planck's constant is approximately 1.055 times 10 to the negative 34th joule-seconds. For the uncertainty principle to not restrict a particle's motion at all, the particle would need to have exactly zero momentum. But if the momentum is exactly zero, the uncertainty in the momentum is zero, which means the uncertainty in the position must be infinite. A particle with exactly zero momentum will be delocalized over all of space with equal probability of being found anywhere. Conversely, a particle localized to a definite position with small uncertainty in position must have correspondingly large uncertainty in momentum, meaning it definitely has non-zero momentum and therefore is definitely moving. The consequences for the behavior of atoms are direct and measurable. The zero-point energy of a quantum harmonic oscillator, the energy the oscillator retains even in its lowest possible energy state, the ground state, is 1/2 times the reduced Planck constant times the oscillator frequency. This is not thermal energy, which can be removed by cooling, but intrinsic quantum mechanical energy that cannot be removed at all. The atom continues to vibrate even at absolute zero because quantum mechanics requires it. If the atom stopped vibrating entirely, it would violate the uncertainty principle by having simultaneously definite position and zero momentum. The zero-point motion of atoms is not merely theoretical. It has been measured directly in several ways. Neutron scattering experiments on solid helium and other light materials at low temperatures reveal the kinetic energy of atoms even as temperature approaches absolute zero, and this energy is greater than zero and matches the quantum mechanical prediction for zero-point energy. The Debye-Waller factor in X-ray crystallography, which describes the reduction in scattering intensity due to thermal and zero-point motion of atoms in crystals, shows a residual value even at absolute zero, that corresponds to zero-point vibration. Helium is the most dramatic example of zero-point motion's physical consequences. Helium, under its own vapor pressure, remains liquid all the way down to absolute zero and only solidifies under pressure of about 25 atmospheres. The reason is that helium's light atomic mass and the weak van der Waals attractions between helium atoms means the zero-point kinetic energy is large enough to prevent the atoms from being localized in a crystal lattice structure, keeping them fluid. Every other element solidifies well above absolute zero because the zero-point energy is insufficient to prevent crystallization, but helium's zero-point energy is so large relative to its interatomic attractions that it remains a liquid until external pressure forces it into a solid. This zero-point motion is not a curiosity of low-temperature physics. It is the manifestation, at the atomic scale, of the fundamental prohibition on stillness that quantum mechanics imposes on all matter. Nothing that exists can ever be completely still, because complete stillness requires zero momentum, and zero momentum combined with finite position violates the uncertainty principle. Motion is not just common in the universe. It is required. The uncertainty principle also applies to time and energy in a complementary way that has additional consequences for the impossibility of stillness. The energy-time uncertainty relation states that the product of the uncertainty in energy and the uncertainty in time cannot be less than the reduced Planck constant divided by 2. For a particle in a definite energy state, the energy uncertainty is zero, which means the time uncertainty is infinite. The state persists indefinitely. But for a particle whose energy is uncertain, the state lasts only for a finite time. This has direct consequences for the quantum vacuum. A quantum field in its ground state cannot have a perfectly defined energy of exactly zero at every point, because such a state would violate the energy-time uncertainty relation. Instead, the energy of the field fluctuates, with brief excursions above the vacuum energy that represent virtual particle creation and annihilation. These fluctuations are real in the sense that they have measurable physical consequences, as demonstrated by the Casimir effect and the Lamb shift. The uncertainty principle also explains why atoms are stable. An electron bound to a proton cannot collapse to the nucleus because localizing the electron to a region the size of the nucleus would require a position uncertainty of roughly 1 femtometer, which by the uncertainty principle requires a momentum uncertainty of at least 100 MeV over c. This corresponds to kinetic energies far greater than the electrostatic attraction of the proton, so the electron's quantum mechanical zero-point motion prevents it from being localized at the nuclear scale. The atom size is set by the balance between the electrostatic attraction, pulling the electron toward the nucleus, and the quantum mechanical pressure of the zero-point kinetic energy pushing it away. Stillness at the atomic scale would collapse atoms, and the universe's atoms have been not still for 13.8 billion years rather than collapsing in a fraction of a second, which is why there are still atoms. The Earth's motion is not simple and not limited to the rotation and orbital motion already mentioned. It is a combination of at least 6 distinct simultaneous motions, each of different character, different time scale, and different consequence, and understanding them together makes the intuition of planetary stillness completely untenable. Earth's rotation on its axis is the fastest of the large-scale motions and the one most directly responsible for the day-night cycle. The rotation period, measured against the background stars rather than against the sun, is approximately 23 hours, 56 minutes, and 4 seconds, called a sidereal day. The solar day, the time from noon to noon, is approximately 4 minutes longer because Earth must rotate slightly more than one full rotation to bring the sun back to the same position in the sky, since Earth has moved slightly in its orbit during that time. The rotation rate is not perfectly constant. Interactions with the Moon through tidal friction are gradually slowing Earth's rotation at a rate of roughly 1.7 milliseconds per century, a process that has been slowing Earth since the Moon formed 4.5 billion years ago. Earth's orbital motion around the Sun is elliptical, not circular, with Earth slightly closer to the Sun in early January, the perihelion, at about 147 million kilometers, and slightly farther in early July, the aphelion, at about 152 million kilometers. The orbital velocity correspondingly varies. Earth moves faster when closer to the Sun and slower when farther, in accordance with Kepler's second law. The difference in orbital speed between perihelion and aphelion is about 1 kilometer per second, not negligible. The Moon's gravitational influence produces a less obvious but measurable motion. Earth actually orbits the Earth-Moon center of mass, which lies about 4,670 kilometers from Earth's center, or about 1,690 kilometers below Earth's surface. This barycentric orbit means that Earth wobbles slightly as the Moon goes around it, describing a small monthly orbit around the barycenter, while both Earth and the Moon together orbit the Sun. Earth's axis is not fixed in space. It precesses, describing a slow cone over a period of approximately 25,772 years due to the gravitational torques exerted by the Sun and Moon on Earth's equatorial bulge. Additionally, the axis wobbles on shorter timescales. The Chandler wobble, with a period of about 433 days, represents a small motion of Earth's rotation pole relative to the geographic surface due to Earth's non-rigidity. And ecliptic plane itself, the plane of Earth's orbit around the Sun, slowly changes its orientation due to the gravitational influences of the other planets. Below the surface, the slow drift of tectonic plates, the cycling of material in the mantle, the liquid flow of the outer core, and the differential rotation of the solid inner core add further layers of motion within the Earth that are detectable with seismographs and satellite measurements. The continent of North America is moving westward at roughly 2 to 3 centimeters per year. Africa and South America are moving apart at roughly 4 centimeters per year. These rates are slow by human standards but amount to kilometers per century and thousands of kilometers per geological epoch. Every stone on every table on Earth participates in all of this motion simultaneously. When we call it still, we mean only that it is not moving relative to its immediate surroundings. The combination of all Earth's motions produces a total velocity relative to a fixed cosmological reference frame that is the vector sum of rotation, orbital motion, galactic orbital motion, and cosmological peculiar velocity. The rotation contribution at mid-latitudes is roughly 300 to 400 meters per second. The orbital contribution around the Sun is about 29,800 meters per second. The galactic orbital contribution is approximately 220,000 meters per second. The cosmological peculiar velocity contribution from the local group's motion toward the Great Attractor is roughly 600,000 meters per second. The total, with vector components depending on direction, is dominated by the cosmological peculiar velocity and amounts to approximately 620 to 700 kilometers per second in the direction toward the Shapley supercluster. These numbers are not merely abstract. They have practical consequences. The timing of atomic clocks depends on velocity due to relativistic time dilation, and the precise values of these velocities must be accounted for in high-precision measurements. The time shown by a GPS satellite clock, which moves at about 3,870 meters per second in its orbit, differs from a ground-based clock by roughly 7 microseconds per day due to the satellite's velocity, an effect that must be corrected for the system to function at meter-level accuracy. Similarly, gravitational potential differences between satellite altitude and ground add another 45 microseconds per day in the other direction. These relativistic corrections to everyday technology are direct consequences of the fact that Earth and its satellites are never still. The rotation of the Earth has been slowing due to tidal friction since the Moon formed, and this deceleration has measurable consequences for the historical record. By measuring the timing of ancient solar eclipses, which depend on exactly where Earth's rotation placed different locations at specific times, and comparing those predictions with eclipse records from ancient Chinese, Babylonian, and Greek sources, scientists have measured the rate of Earth's rotational deceleration and confirmed that days were shorter in the ancient past. The Sun is a star about 26,000 light-years from the center of the Milky Way galaxy, embedded in the disk of the galaxy in a relatively ordinary location in what is called the Orion Arm or Orion Spur, a minor spiral arm feature between two of the galaxy's major arms. The Sun is not stationary in the galaxy. It orbits the galactic center at a speed of approximately 220 kilometers per second, making it one of the faster objects in the human experience to travel continuously in the same direction, though of course that direction is always changing as the orbit curves. One complete orbit of the Sun around the galactic center takes approximately 225 to 250 million years. This duration is sometimes called a galactic year or a cosmic year. The last time the Sun was at its current position in its galactic orbit, the dominant land animals on Earth were the earliest dinosaurs in the late Triassic period. The time before that, the Sun was at this position during the Permian period, just after the most severe mass extinction in Earth's history. In the roughly 4.6 billion years since the solar system formed, it has completed about 20 galactic orbits, covering a total path length of roughly 150,000 light-years around a galaxy. The Sun's orbit around the galactic center is not a simple flat ellipse. The Sun bobs up and down relative to the galactic plane as it orbits, crossing through the plane roughly every 32 to 35 million years. The plane of the galaxy has a higher density of molecular clouds, stellar nurseries, and massive stars, and there is ongoing research into whether the solar system's periodic passages through the galactic plane correlate with periods of increased comet bombardment of the inner solar system, possibly linked to extinction events, though this connection remains controversial. The shape of the Sun's galactic orbit is also not a perfect circle. The galaxy's mass distribution is not perfectly symmetric, and the Sun's orbit has a modest eccentricity, bringing it somewhat closer to and then farther from the galactic center over the course of each orbit. As the Sun moves through different regions of the galaxy, it passes through regions of different stellar density, different gas and dust density, and different gravitational influences from spiral arm passages. The speed of 220 kilometers per second relative to the galactic center is itself something that must be assessed relative to a reference frame, and the choice of reference frame makes a significant difference to how the motion is described. Relative to the local standard of rest, a reference frame defined by the average motion of stars in the solar neighborhood, the Sun moves at about 20 kilometers per second in a specific direction called the solar apex, in the direction of the constellation Hercules. This peculiar velocity, the Sun's motion relative to its neighbors, reflects the Sun's individual orbital characteristics being slightly different from the average. None of the objects in the solar system, from the smallest dust grain to the Sun itself, has ever been still relative to any fixed reference point. They have all been in continuous motion since they coalesced from the rotating disk of gas and dust that formed the solar system, inheriting that rotation and orbital motion as their permanent kinematic inheritance. The path of the solar system through the galaxy over its lifetime is not a simple closed orbit that traces and retraces the same path. The galaxy is not a perfectly symmetric mass distribution, and the gravitational influences of the spiral arms, the galactic bar, molecular cloud complexes, and other stellar mass concentrations perturb the solar system's orbit from any simple ellipse. The result is a rosette-shaped path that slowly precesses around the galactic center, sometimes dipping closer, sometimes reaching farther, while bobbing above and below the galactic plane. The Sun's current location in the galactic disk is slightly above the midplane, by about 56 light-years, moving northward relative to the plane at roughly 7 kilometers per second. The Sun crossed the midplane approximately 2 million years ago, and will reach its maximum northern excursion of about 230 light-years above the plane in roughly 14 million years before beginning to descend back through the plane again. This oscillation is superimposed on the orbital motion around the galactic center, creating the three-dimensional spiral helix path that the Sun actually traces. The implications for Earth's environment over geological time are potentially significant. When the solar system is at different galactic radii or in different environments within the galaxy, the cosmic ray flux and other space weather conditions change. The passage through spiral arms, which contain higher densities of gas, dust, and young massive stars that produce more cosmic rays and are more likely to have nearby supernova explosions, has been proposed as a possible driver of periodic variations in Earth's climate and even in the frequency of mass extinctions over geological time. These hypotheses are controversial and not conclusively established, but they reflect the real physical fact that the solar system's galactic journey exposes Earth to varying environments on timescales of tens to hundreds of millions of years. The Milky Way galaxy as a whole is not stationary in the universe. It is moving relative to other galaxies, participating in the gravitational dynamics of the local group, and pulled by and toward larger concentrations of mass scattered through the cosmic web. Measuring the Milky Way's velocity is more complex than measuring the velocity of individual stars because we are inside the galaxy, but several independent lines of evidence now give a consistent picture. The most direct measurement comes from observations of the cosmic microwave background, the thermal radiation left over from the epoch of recombination about 380,000 years after the Big Bang, which permeates the universe with extraordinary uniformity. If the observer is moving relative to the frame in which this radiation is isotropic, the radiation appears slightly blue-shifted in the direction of motion and slightly red-shifted in the opposite direction, a dipole anisotropy in the CMB of temperature. Measuring this dipole gives the observer's velocity relative to the CMB rest frame, which is the best available approximation to the cosmological rest frame. The measured dipole corresponds to the solar system moving at approximately 369 kilometers per second toward the constellation Leo. After subtracting the known motion of the Earth around the Sun and the Sun's motion within the Milky Way, the remaining velocity corresponds to the Milky Way's peculiar motion relative to the CMB rest frame. The Milky Way, along with the rest of the local group of galaxies, is moving at roughly 620 kilometers per second in the direction of the Centaurus and Hydra constellations toward a large concentration of mass called the Great Attractor. The Great Attractor is a region of enhanced density at roughly 150 to 250 million light-years distance that has been attracting the local group and nearby galaxy groups and clusters for billions of years. The core of the Great Attractor region coincides with a rich galaxy cluster called Abell 3627. Beyond the Great Attractor, at roughly 650 million light-years, is an even larger concentration of mass called the Shapley supercluster, which appears to be a secondary gravitational influence. Disentangling the contributions of these various mass concentrations to the local group's observed velocity requires detailed modeling of the mass distribution inferred from galaxy redshift surveys. The Andromeda Galaxy, the Milky Way's nearest large neighbor and partner in the local group, is approaching the Milky Way at roughly 110 kilometers per second in radial velocity, though the transverse component of its velocity is less well known. The two galaxies will begin interacting gravitationally in about 4 to 5 billion years, and will eventually merge over a timescale of several billion years more, producing a new, larger elliptical galaxy, sometimes called Milkomeda. This motion, two galaxies each moving and together being pulled toward a cosmic merger that will reshape both of them, is not an aberration in an otherwise static universe. It is the universe doing what it has always done, moving. The peculiar velocity of the local group relative to the CMB has been measured with increasing precision as CMB observations have improved. The Planck satellite's all-sky map of the CMB, published in a series of data releases from 2013 onward, measured the dipole anisotropy with high precision, finding a velocity of approximately 369 kilometers per second in the direction of galactic coordinates pointing toward the constellation crater. This includes the contribution from Earth's orbital motion around the Sun and the Sun's motion within the Milky Way, which must be subtracted to get the Milky Way's contribution, and then the Milky Way's motion within the local group must be subtracted to get the local group's contribution. The Large Magellanic Cloud and Small Magellanic Cloud, the two largest satellite galaxies of the Milky Way, are themselves moving. The Large Magellanic Cloud is at roughly 160,000 light-years, and is moving relative to the Milky Way at about 300 kilometers per second. Gaia-proper motion measurements have shown that both Magellanic Clouds may be on first approach to the Milky Way rather than being long-term satellites, based on their high velocities relative to the Milky Way's escape velocity. The clouds may have been traveling together as a binary pair for billions of years before being captured by the Milky Way's gravity, and they may be on hyperbolic orbits that will eventually take them away rather than bound orbits that keep them as permanent satellites. The Andromeda-Milky Way merger, expected in roughly 4 to 5 billion years, will produce a merger remnant whose structure is predictable in broad terms from numerical simulations of galaxy mergers. The Sun's orbit in the final merged galaxy is expected to be scattered significantly, with the Sun ending up at a range of possible distances from the new galactic center. The Sun's neighborhood will be disrupted, but the Sun itself and the solar system will almost certainly survive the merger intact, Stellar collisions during galaxy mergers are extremely rare because of the vast distances between stars. The large-scale motion of galaxies in a local universe reveals the universe's bulk flow structure, a pattern of coherent motion in which groups and clusters of galaxies move in common directions as they are pulled by concentrations of mass distributed through the cosmic web. Understanding this bulk flow, and the great attractor that dominates it locally, is one of the central problems in observational cosmology and provides some of the most compelling evidence for the universality of cosmic motion. The discovery that the local group and nearby galaxy clusters were all moving in the same direction at similar speeds was made in the 1970s and early 1980s through measurements of galaxy peculiar velocities, the difference between a galaxy's observed recessional velocity and the velocity expected purely from the Hubble expansion. When these peculiar velocities were mapped for large numbers of galaxies, it became clear that there was a coherent flow, a dipole pattern of velocities, centered on a direction in the southern sky. The region toward which this flow was directed was partially obscured by the Milky Way's own disk, making early observations difficult and leading to considerable debate about the nature and location of the attractor. X-ray observations and infrared surveys that could penetrate the galactic plane revealed that the flow was directed toward a large concentration of galaxies in the Norma cluster region, part of a significant overdensity of mass later characterized as the Great Attractor. Subsequent surveys revealed that this concentration itself sits on the outskirts of the Shapley supercluster, an even more massive structure at greater distance. The Laniakea supercluster, delineated in 2014 by Brent Tully and colleagues using a technique that maps galaxy peculiar velocities to identify the boundaries of gravitational basins of attraction, define a region of space roughly 520 million light-years across within which all galaxy flows converge. The Milky Way sits near the outskirts of Laniakea, which contains on the order of 100,000 galaxies, including the Virgo cluster, the Great Attractor concentration, and the Shapley supercluster as its most massive components. The name Laniakea comes from the Hawaiian words for immeasurable heaven, reflecting both the scale and the traditional navigation knowledge of Polynesian astronomers. The Laniakea picture is dynamic in a specific sense that illuminates the nature of cosmic motion. The boundaries of Laniakea are not physical walls, but the ridges in the gravitational landscape where galaxy flows diverge outward toward different attractors. Galaxies on the boundary of Laniakea are being pulled roughly equally by the Laniakea concentration and by neighboring structures, and some will eventually fall toward Laniakea while others will fall away. The structure is not stable over cosmological time. The accelerating expansion of the universe, driven by dark energy, is progressively overcoming the gravitational coherence that defines Laniakea, and in the far future, the supercluster will be dispersed by the expansion. Every galaxy in and around Laniakea is moving. Every galaxy outside it is moving. The universe provides no reference point, no fixed anchor against which other things move while it remains still. Everything moves relative to everything else, pulled by gravity, driven by momentum imparted at the Big Bang, subject to the accelerating expansion that dark energy maintains. The observational challenge of understanding the Great Attractor and the larger-scale flow structure requires measuring the peculiar velocities of large numbers of galaxies. This requires independent distance measurements for each galaxy, separate from the distance inferred from its redshift, because the redshift combines the Hubble expansion velocity with the peculiar velocity, and you need to subtract one to measure the other. Techniques for measuring galaxy distances include the Tully-Fisher relation for spiral galaxies, which relates the rotation speed of a galaxy to its luminosity, and the fundamental plane for elliptical galaxies, which relates the effective radius, surface brightness, and velocity dispersion. Both methods have scatter at the 20% level, requiring large samples of galaxies to measure the flow pattern statistically. The Cosmic Flows program, a long-running project led by Brent Tully and collaborators, has assembled distance catalogs containing thousands and eventually tens of thousands of galaxies with independent distance measurements. These catalogs allow the peculiar velocity field to be mapped and reconstructed over a volume extending to several hundred million light-years, revealing the complex three-dimensional flow pattern produced by the distribution of matter. The flow maps show clear convergence toward the Great Attractor region and evidence for additional attractors and voids that deflect the flow in various directions. Comparison of the observed peculiar velocity field with predictions based on the galaxy density field observed in redshift surveys provides tests of the cosmological model. The relationship between the density field and the velocity field it produces is predicted by gravitational instability theory. Denser regions exert more gravitational attraction and produce stronger convergent flows. The amplitude of the predicted flows depends on the growth rate of structure, which in turn depends on the cosmological model, particularly the matter density and the properties of dark energy. The expansion of the universe is perhaps the most dramatic and most frequently misunderstood form of motion in the cosmos. It is not motion in the sense of galaxies flying through space away from each other, like pieces of a bomb blast. It is the expansion of the space between galaxies, the growth of the metric of space-time itself, which carries the galaxies apart as a passenger in a train is carried by the train rather than propelling themselves. Edwin Hubble's 1929 observation that distant galaxies are receding from us, with recession velocity proportional to distance, established the expansion of the universe as an observational fact. The constant of proportionality, a Hubble constant, is currently measured at approximately 67 to 73 kilometers per second per megaparsec, depending on the measurement method used, and its precise value has become one of the central tensions in modern cosmology as different measurement techniques give slightly different answers. For our purposes, the relevant point is that for every megaparsec of additional distance, the recession velocity increases by this amount, meaning galaxies far enough away recede faster than the speed of light. This does not violate special relativity because the recession velocity is not the velocity of galaxies through space, but the rate at which the distance between them and us grows due to the expansion of space itself. Special relativity restricts velocities through space. It does not restrict the rate at which space can expand. In the language of general relativity, the scale factor of the universe, a quantity that describes how all distances change over time, is increasing, and the rate of its increase is what the Hubble constant measures. In 1998, two independent teams observing distant Type Ia supernovae discovered that the expansion of the universe is not merely continuing but is accelerating. Distant supernovae appeared fainter than expected, meaning they were farther away than a decelerating or even uniformly expanding universe would predict. The acceleration is attributed to a component of the universe's energy called dark energy, best described by a positive cosmological constant, which acts as a repulsive influence distributed uniformly throughout space. Dark energy currently constitutes roughly 68% of the total energy content of the observable universe, with dark matter contributing about 27% and ordinary baryonic matter only about 5%. The accelerating expansion means that galaxies beyond a certain distance, the cosmic event horizon at roughly 16 billion light-years, are receding from us faster than light and will never be reachable by any signal we send. The observable universe is therefore a shrinking fraction of the total universe. In the far future, all galaxies beyond our local group will have been swept beyond the event horizon, and the universe will appear increasingly empty even as it continues to expand. The motion of cosmic expansion is permanent, accelerating, and encompasses everything outside our gravitational neighborhood. The distinction between the expansion of space and motion through space has sometimes been described in ways that are confusing, so it is worth being precise. The expansion of the universe does not mean that atoms and molecules within solid objects are expanding. The electromagnetic forces binding matter together are strong enough to resist the very gentle tendency of a local metric to expand, so objects bound by electromagnetic or gravitational forces maintain their sizes. Only on scales where gravitational attraction or other forces do not bind the structures together does the expansion become dominant. The threshold between gravitationally bound and expansion-dominated is roughly the scale of galaxy groups and clusters. The Milky Way and the other galaxies of the local group are gravitationally bound and will not be separated by the expansion. They will eventually merge. The Virgo cluster, containing thousands of galaxies, is gravitationally bound and is not expanding. But the distances between galaxy clusters and superclusters, structures that are not gravitationally bound to each other, are increasing with the expansion. The future universe will contain isolated islands of bound matter, galaxy clusters, and groups, separated by ever-increasing voids. The cosmic microwave background temperatures decrease with expansion provides a clock for the universe's history. The CMB temperature today is 2.725 Kelvin. When the CMB was emitted at recombination, approximately 380,000 years after the Big Bang, the universe's temperature was about 3,000 Kelvin, meaning the universe has expanded by a factor of roughly 1,100 in linear scale since recombination. In the far future, the CMB temperature will continue to decrease at 10 times the current age of the universe. Assuming the expansion rate remains roughly constant, the CMB temperature will be roughly 0.27 Kelvin. The universe will never be at zero temperature. The CMB will asymptotically approach but never reach absolute zero as the expansion continues indefinitely. Among all the motions in the universe, the motion of light stands apart as uniquely invariant. Every other moving thing has a velocity that depends on the reference frame from which it is measured. A ball thrown at 10 meters per second from a train moving at 30 meters per second moves at 40 meters per second relative to the ground. The moon moves relative to Earth, Earth relative to the sun relative to the galaxy. All of these velocities are defined relative to something else and have different values in different reference frames. Light is completely different. The speed of light in vacuum is approximately 299,792,458 meters per second, and this is the same value measured by every observer in every inertial reference frame, regardless of the observer's velocity, regardless of the velocity of the source, regardless of the direction. This counterintuitive constancy of the speed of light was the experimental fact that Einstein took of the postulate of special relativity, and that led directly to the equations of the Lorentz transformation and to the entire framework of relativistic physics. The reason for this constancy is not fully intuitive, but is deeply connected to the nature of spacetime. Light is a disturbance in the electromagnetic field, and the equations governing the electromagnetic field, Maxwell's equations, contain within them a specific propagation speed that depends only on the electric permittivity and magnetic permeability of vacuum, both of which are fundamental constants of nature. The propagation speed works out to exactly c, and since the laws of physics are the same in all inertial frames, the speed of light must be the same in all inertial frames. The implication for the question of stillness is direct and absolute. Light cannot be still. There is no reference frame in which a photon is at rest. If you could somehow accelerate to near the speed of light in the same direction as a photon, the photon would still be moving away from you at c. The concept of a still photon is simply not a coherent physical concept. A photon exists only in motion, always at sea, never at rest. More than this, the impossibility of slowing light to a stop reflects the nature of light as a massless particle. Massless particles must travel at exactly c in vacuum. This is a consequence of the relativistic energy-momentum relation. A particle with zero rest mass has kinetic energy equal to its momentum times c, and for this relationship to hold and for the particle to carry any energy at all, it must travel at exactly c. Slowing a massless particle to below c would require giving it rest mass, changing its fundamental nature. A photon that stopped moving would not be a slow photon. It would not be a photon at all. Even in media where light propagates more slowly, the slowdown is not truly a slowdown of the photons, but a different phenomenon. Individual photons in a material are absorbed and re-emitted by atoms in the medium, and the sum of these multiple absorption-re-emission events with their delays produces the appearance of slower light propagation. Between each absorption and emission, each photon travels at exactly c. Light's motion is perhaps the clearest example of a category of motion that is not an incidental feature but a defining property. Light is motion. To say a photon is at rest is like saying a triangle has four sides. The concept violates the definition. The invariance of the speed of light has been tested with extraordinary precision in many experimental contexts. One of the most precise tests uses laser interferometry to compare the speed of light in different directions, testing whether Earth's motion through space produces any anisotropy in the speed of light. Modern versions of the Michelson-Morley experiment, using stabilized laser cavities rather than mechanical mirrors, have achieved sensitivities that constrain any anisotropy of the speed of light to less than 10 to the minus 22 of C, essentially 17 orders of magnitude better than the original Michelson-Morley experiment. No anisotropy has been detected. The relationship between light's constant speed and the structure of special relativity produces one of its most counterintuitive predictions, the relativity of simultaneity. If two events are separated in space and one observer judges them to be simultaneous, a moving observer will in general disagree. One event will appear to precede the other, with the ordering depending on the direction of the observer's motion. This is not a perceptual illusion or a measurement artifact. It is a genuine physical fact that follows from the constancy of C. Two observers in relative motion looking at the same pair of space-like separated events will in general disagree about their temporal ordering, and both are right in their own reference frames. This relativity of simultaneity means that the concept of the present moment, what is happening right now throughout the universe, is observer-dependent. There is no universal now. Different observers in relative motion slice spacetime differently into spatial slices labeled by their time coordinate, and these slices do not coincide. Simultaneity is a coordinate-dependent notion, not an invariant physical one. The light barrier is the mechanism that enforces this relativity of simultaneity. Because no signal can travel faster than light, there is no way for two space-like separated events to be objectively ordered in time, making the temporal ordering observer-dependent. Within atoms, the motion of electrons is one of the most consequential and most misrepresented phenomena in all of science. The model of electrons as tiny particles orbiting the nucleus like planets orbiting the sun, while useful as an introductory image, is deeply wrong in ways that matter for understanding why atomic electrons are never still and why they are not still in a way that classical particles in orbits would be still. The Bohr model of the atom, proposed by Niels Bohr in 1913, did picture electrons as orbiting the nucleus in discrete circular paths at fixed distances, with the angular momentum of each orbit being an integer multiple of the reduced Planck constant. This model correctly predicted the energy levels of hydrogen and was a significant advance over earlier models, but it had a fatal problem. An electron in circular orbit is accelerating toward the center, and an accelerating charged particle should, according to Maxwell's equations, radiate electromagnetic energy continuously. This energy loss would cause the electron to spiral into the nucleus in a fraction of a second, making stable atoms impossible. Clearly, atoms are stable, so something was fundamentally wrong with the picture. Quantum mechanics resolved this by abandoning the picture of electrons as particles in definite orbits. In the quantum mechanical description, electrons exist in stationary states described by wave functions, mathematical objects that encode the probability of finding the electron at any given location if a measurement were made. These wave functions are not waves of the electron's position but waves of probability amplitude, and they are solutions to the Schrödinger equation for the specific potential energy of the electron in the nuclear electric field. The stationary states of hydrogen, the energy eigenstates, are the familiar atomic orbitals, 1s, 2s, 2p, and so on. An electron in one of these states does not radiate and does not spiral into the nucleus because its energy is precisely defined and it has no lower energy state to fall into while staying in the atom. But the electron is emphatically not still in any classical sense. Its wave function extends throughout a region of space, meaning if you measure its position, you might find it close to the nucleus or quite far from it, depending on the specific orbital. The probability of finding the electron at different positions is given by the square of the wave function, and this probability is not concentrated at a single point. Furthermore, the uncertainty principle operates here exactly as described earlier. An electron with a definite energy and a definite angular momentum has indefinite position and therefore indefinite momentum. Measuring the momentum of an electron in an atomic orbital gives a random result drawn from a probability distribution, and that momentum is never zero. The electron is always moving in the sense that its momentum is always non-zero, even though the concept of a trajectory, a definite path in space, does not apply. The reality of this quantum motion has physical consequences that are macroscopically important. The size of atoms, the fact that they do not collapse, the chemical properties of elements, the formation of molecular bonds, all depend crucially on the quantum mechanical motion of electrons in their orbitals. Chemistry is, at its foundation, the science of electron motion. The energy contained in the quantum mechanical motion of electrons and atoms is not small. The typical energy of an electron in a hydrogen atom's ground state is about 13.6 electron volts, which sets the scale for the energy involved in atomic physics and chemistry. This is the energy that must be supplied to ionize hydrogen, to remove the electron from the atom entirely. The kinetic energy contribution to this total energy is, by the virial theorem for Coulomb potential, half the magnitude of the total energy, or about 6.8 electron volts. The velocity corresponding to this kinetic energy is roughly 2 million meters per second, about 0.7% of the speed of light. Even this semi-classical estimate understates the quantum mechanical reality. The electron's momentum in the ground state of hydrogen has an expectation value of 0 because the wave function is spherically symmetric and the electron is equally likely to be moving in any direction. But the expectation value of momentum squared is not 0. The root mean square momentum corresponds to speeds of about 2 million meters per second. And the uncertainty in the momentum is of the same order, meaning that any given measurement of the electron's speed gives a result near this value, but scattered by quantum uncertainty. The kinetic energy of electron motion is the source of the energy released in chemical reactions. When hydrogen and oxygen combine to form water, the electrons rearrange their quantum mechanical orbits from configurations appropriate to the separate atoms to configurations appropriate to the water molecule. The energy difference between these configurations, about 2.5 electron volts per water molecule formed, is released as heat. The chemical energy in every fuel, from wood to gasoline to hydrogen, is ultimately the kinetic energy of electrons in quantum mechanical states, released when those electrons are rearranged into lower energy configurations. The quantum vacuum, the lowest energy state of a quantum field, is not a state of nothing. It is not even a state of minimal something. It is a seething, dynamic, fundamentally active state in which energy fluctuates continuously. Particles and antiparticles appear and disappear on timescales too short to violate energy conservation, and the electromagnetic field and all other quantum fields oscillate with zero-point energy that cannot be removed or suppressed. The existence of vacuum fluctuations is a direct consequence of the uncertainty principle applied to quantum fields. A quantum field at each point in space is like a quantum harmonic oscillator, and as demonstrated earlier, quantum harmonic oscillators retain zero-point energy in the ground state. The quantum vacuum is the ground state of all quantum fields simultaneously, and each field's ground state contributes its zero-point oscillations. The vacuum is not still. It vibrates with the irreducible minimum energy that quantum mechanics permits. Vacuum fluctuations are not merely theoretical. They have been measured in several ways, the most famous being the Casimir effect. When two uncharged parallel conducting plates are placed very close together, with a small gap between them, the conducting boundary conditions on the electromagnetic field inside the gap restrict the modes of vacuum fluctuation that can exist between the plates to those with wavelengths that fit the gap. Outside the plates, all modes are available. The result is that the zero-point energy density between the plates is slightly lower than outside, creating a pressure imbalance that pushes the plates together. The Casimir force was first predicted by Hendrik Casimir in 1948 and has been measured experimentally with increasing precision since the 1990s, confirming the theoretical prediction to better than 1%. Vacuum fluctuations also contribute to the Lamb shift, a tiny difference in the energy levels of the 2s and 2p states of hydrogen that cannot be explained by the Dirac equation alone but requires accounting for the quantum electrodynamic effects of the electron interacting with virtual photons from the vacuum. Willis Lamb measured this shift in 1947, earning the Nobel Prize in 1955, and its explanation by quantum electrodynamics was a major triumph of that theory. The spontaneous emission of light by excited atoms is another manifestation of vacuum motion. A classical analysis would suggest that an excited atom, in the absence of any electromagnetic radiation, should remain in its excited state indefinitely. But quantum electrodynamics shows that the electromagnetic vacuum fluctuations tickle the excited atom, stimulating it to emit a photon and drop to its ground state. The vacuum, far from being a passive background, actively participates in atomic physics. The enormous energy density of vacuum fluctuations, estimated to be orders of magnitude larger than the observed dark energy density, is one of the most profound unsolved problems in theoretical physics, sometimes called the cosmological constant problem or the vacuum catastrophe. Whatever its ultimate resolution, the vacuum's non-zero energy density confirms that space itself is not still, not empty, and not passive. The magnitude of vacuum energy is one of the most embarrassing discrepancies in theoretical physics. Quantum field theory, using the most straightforward calculation of the sum of zero-point energies of all field modes, gives a vacuum energy density of roughly 10 to the 74th grams per cubic centimeter, or equivalently an energy density corresponding to a cosmological constant far larger than the one inferred from cosmological observations. The observed dark energy density, which is what the cosmological constant corresponds to physically, is roughly 10 to the minus 29 grams per cubic centimeter. The discrepancy between the naive quantum field theory calculation and the observed value is roughly 120 orders of magnitude. This mismatch, sometimes called the cosmological constant problem or the vacuum catastrophe, is widely regarded as the most severe unexplained discrepancy in all of physics. It suggests that some cancellation mechanism reduces the naive vacuum energy to a value many orders of magnitude smaller, but no satisfactory explanation for this cancellation has been found. The problem is so severe that it suggests current theories are missing something fundamental about the nature of vacuum energy and its gravitational effects. The practical reality of vacuum fluctuations, confirmed at the level of experimental physics by the Casimir effect and radiative corrections to atomic energy levels, is not in question. What is uncertain is how to properly calculate the gravitational effects of this energy, which requires a unified theory of quantum mechanics and general relativity that does not yet exist. In the absence of such a theory, the vacuum energy is a source of observed physical effects, including the Casimir force and spontaneous emission, but its contribution to the cosmological constant remains opaque, one of the frontier problems of fundamental physics. Absolute 0 Kelvin, negative 273.15 degrees Celsius, is the lower bound of the temperature scale, the temperature at which thermal motion would cease if the third law of thermodynamics permitted it to be reached. The third law states that the entropy of a perfect crystal at absolute zero is zero, which combined with the second law implies that reaching absolute zero would require removing an infinite amount of entropy from a system, an impossible task in any finite number of steps. The third law of thermodynamics was established empirically by Walther and Nernst in the early 20th century, and has a simple physical basis. As temperature decreases, fewer and fewer microstates are accessible to the system, and the system's configuration becomes increasingly constrained to the lowest energy configurations. At absolute zero, the system would be in a perfectly ordered state with exactly one accessible microstate. But quantum mechanics ensures that this perfectly ordered state still has zero-point energy, still has zero-point motion, and is therefore not truly still even in the hypothetical limit. Reaching absolute zero is impossible in practice for a more immediate reason than the third law. Every cooling process requires a colder reservoir to absorb the heat that is removed from the system being cooled. To cool a system to absolute zero would require a reservoir at absolute zero, which requires that reservoir to itself have been cooled to absolute zero first. The logical chain regresses without end. The coldest temperatures ever achieved in laboratories, in atomic traps and Bose-Einstein condensate experiments, are measured in billionths or even trillionths of a Kelvin, but these achievements approach absolute zero asymptotically, never reaching it. The coldest naturally occurring places in the observable universe are the Boomerang Nebula, a protoplanetary nebula approximately 5,000 light-years away, where temperatures as low as 1 Kelvin have been measured, and certain regions of space far from any galaxy where the ambient temperature is set by the cosmic microwave background at 2.725 Kelvin. Nothing in the observable universe is at absolute zero. What would happen at absolute zero, were it achievable, is instructive. The thermal motion of atoms would vanish, but the zero-point quantum mechanical motion would remain, as demonstrated by liquid helium. All gases except helium would have already condensed to solids long before approaching absolute zero. The atoms in the resulting perfect crystals would still oscillate about their lattice positions with zero-point energy. The electrons in the atoms would still occupy their quantum orbitals with non-zero kinetic energy. The nuclei would still be governed by the strong nuclear force, which itself is mediated by the exchange of pions with kinetic energy, continuous motion at the nuclear scale. The universe is not getting close to absolute zero in any global sense. The current temperature of the cosmic background radiation is 2.725 Kelvin. As the universe expands, this temperature decreases inversely with a scale factor. So in the far future, the universe will be much colder. But it will approach absolute zero asymptotically, never reaching it, in precisely the same way that all real cooling processes approach absolute zero without achieving it. The motion encoded in quantum mechanics is permanent. The practical techniques for cooling matter to the vicinity of absolute zero have advanced enormously since the first liquefaction of helium by Heike Kamerlingh-Onnes in 1908. Modern dilution refrigerators, which use the difference in entropy between the helium-3-rich and helium-4-rich phases of a liquid helium mixture, routinely achieve temperatures of a few millikelvin, a few thousandths of a Kelvin. Laser cooling and magnetic evaporative cooling of dilute atomic gases can reach temperatures below a microkelvin, and careful variations of these techniques have produced temperatures as low as a few tens of picokelvin, tens of trillionths of a Kelvin, in experiments with ultra-cold atomic gases. At these extremely low temperatures, quantum mechanical effects that are negligible at ordinary temperatures become dominant. Bose-Einstein condensation, the phenomenon in which a macroscopic fraction of the atoms in a Bose gas fall into the same quantum state when cooled below a critical temperature, was predicted by Satyendra Nath Bose and Albert Einstein in 1924 and first observed experimentally in 1995 by Eric Cornell and Carl Wieman using rubidium atoms, work that earned them the Nobel Prize in Physics in 2001. In a Bose-Einstein condensate, the atoms behave as a single quantum mechanical entity rather than individual classical particles, and the wave-like properties of matter that are normally buried in the thermal noise become macroscopically apparent. Even in a Bose-Einstein condensate at a temperature of a few nanokelvin, the atoms have not stopped moving. Their thermal velocity is indeed extremely small, but their quantum mechanical zero-point motion means they are still vibrating in the trapping potential with the irreducible minimum energy that quantum mechanics allows. The condensate is the quantum ground state of the trapped system, not a state of classical rest. The atoms are as cold as they can possibly be while still being trapped, and they are still moving. Rotation, the circular form of motion, is one of the most ubiquitous physical phenomena in the universe, arising from the conservation of angular momentum and the dynamics of gravitational collapse. Understanding why spinning objects are so universal requires understanding the origin of angular momentum and why it is so difficult to eliminate. Angular momentum is a conserved quantity in physics. For a system with no external torques, the total angular momentum cannot change. This conservation law arises mathematically from the rotational symmetry of the laws of physics. Because the fundamental laws do not prefer any particular direction in space, angular momentum cannot be created or destroyed by internal processes. This is an exact conservation law, to the same precision as the conservation of energy and linear momentum. The implication is that any angular momentum present when a system forms is inherited by whatever that system becomes. The interstellar gas clouds from which stars and planetary systems form are not in perfect solid-body rotation, but they have some net angular momentum from the differential motions of their constituent gas parcels. As such a cloud collapses under gravity, the cloud shrinks in radius while conserving angular momentum. Since angular momentum is mass times velocity times radius, if radius decreases while mass and angular momentum are conserved, velocity must increase. A collapse from interstellar scales to stellar scales involves factors of billions to trillions in radius reduction, with proportional increases in rotation rate. The result is that essentially every astronomical body that forms from the collapse of a larger structure is spinning, often rapidly. Neutron stars, formed from the core collapse of massive stars in supernova explosions, spin at rates from once per second to hundreds of times per second. Young pulsars, newly formed neutron stars, spin especially fast because the collapse preserves the angular momentum of the original stellar core while compressing it to stellar scale. The Crab pulsar, the neutron star at the center of the Crab Nebula formed in a supernova explosion observed in 1054 CE, rotates approximately 30 times per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates at approximately 716 times per second, meaning a point on its equator is moving at roughly a quarter of the speed of light. Planets spin for the same reason. They formed from rotating material and inherited angular momentum from that formation. Earth rotates once per day. Jupiter, much more massive, rotates once every 10 hours. Asteroids and smaller bodies spin with a wide range of rates, from nearly stationary to rotations in seconds for the smallest rapidly spinning objects. Gas giant planets have been found around other stars whose equatorial rotation speeds have been measured by observations of their spectral line broadening, and they rotate rapidly as expected from angular momentum conservation. Even at the quantum level, particles carry intrinsic angular momentum called spin, a fundamentally quantum mechanical property with no classical analog. Electrons have spin 1/2 in units of the reduced Planck constant. Photons have spin 1. Quarks, the constituents of protons and neutrons, have spin 1/2. This intrinsic spin is not the result of a particle physically rotating in space. It is an intrinsic quantum property analogous to charge, a permanent attribute of the particle that cannot be removed or reduced. Spin is angular momentum without rotation, and it is universal among quantum particles. The specific angular momenta of various astronomical objects span an enormous range. A slowly rotating asteroid with a period of a day or two has a very low angular momentum per unit mass. Earth, spinning once per day, has a higher specific angular momentum. The Sun rotates once every 25 days at its equator, and its specific angular momentum is much lower than that of a typical young star, reflecting the angular momentum redistribution that occurred during the Sun's formation. Young T Tauri stars, protostars in the late stages of formation, often rotate much faster than the Sun, with periods of a few days. Neutron stars and pulsars take this to an extreme. The Crab pulsar's rotation at 30 times per second and the fastest millisecond pulsars at over 700 times per second represent the conservation of enormous amounts of angular momentum from the collapsed stellar core. The progenitor star, with a core perhaps 10,000 kilometers in radius before collapse, had its angular momentum conserved as it collapsed to a neutron star 10 to 12 kilometers in radius, a factor of 1,000 in radius. Since angular momentum equals moment of inertia times angular velocity, and moment of inertia scales as the radius squared, the angular velocity scales inversely as the radius squared, 1,000 squared equals 1,000,000, meaning the rotation rate can increase by a factor of up to 1,000,000 during the collapse. Stellar cores rotating once per day before collapse would emerge as neutron stars rotating 1,000,000 times faster, in the millisecond range. At the galactic scale, the rotation of spiral galaxies reflects the angular momentum of the gas cloud from which they formed. The angular momentum of the Milky Way, dominated by the disk, is approximately 10 to the 67th kilogram meters squared per second. This is an enormous number, and it has been slowly redistributed over the galaxy's lifetime through the transfer of angular momentum from the bar and spiral arms to the outer disk and through interactions with satellite galaxies. But the total is conserved. The continuous, never-resting thermal motion of atoms and molecules was confirmed decisively in 1827 not by a physicist but by a Scottish botanist named Robert Brown. Brown was examining pollen grains suspended in water under a microscope when he noticed that the grains were not sitting still as expected but jittered continuously in what appeared to be random, directionless motion. Initially, Brown wondered whether this motion might be a sign of life in the pollen, perhaps some vital force animating the grains. He tested this hypothesis by examining grains of non-biological material, including dust from volcanic rock and rock crystals, and found the same persistent jittering. The motion was real, universal, and inexplicable by the physics of the time. The motion Brown observed, now called Brownian motion, was correctly explained in 1905 by Albert Einstein in one of his 4 famous papers published in that miraculous year. Einstein showed that Brownian motion arises from the continuous bombardment of the visible particle by the invisible molecules of the surrounding fluid. Each collision imparts a tiny impulse to the particle, and the random, asymmetric accumulation of many such impulses produces the jittering visible under the microscope. Einstein derived a quantitative relationship between the mean square displacement of the particle, the temperature of the fluid, the size of the particle, and the viscosity of the fluid. This relationship was confirmed experimentally by Jean Perrin in 1908 and 1909, in work that earned Perrin the Nobel Prize in Physics in 1926. Perrin's measurements confirmed Einstein's formula with high precision and, crucially, allowed him to determine Avogadro's number, the number of molecules in a mole of any substance, to a value consistent with independent determinations. This was definitive confirmation that matter is composed of discrete molecules, settling a question that had been debated among physicists and chemists for decades, and it simultaneously confirmed that those molecules are in constant, never-ceasing thermal motion. The mathematics of Brownian motion developed by Einstein was independently and simultaneously developed by Marian Smoluchowski, and the theoretical framework was later generalized by Paul Langevin into what is now called the Langevin equation. This framework describes the motion of a particle subject to both a systematic force and a random stochastic force, representing the molecular bombardment. The Langevin equation and its generalizations are now among the most widely used equations in physics, applied to problems ranging from the diffusion of molecules in biological cells to the motion of financial assets in markets to the noise in electronic circuits. The lesson of Brownian motion is that the visible world of everyday experience is immersed in an invisible world of molecular motion that never rests and never averages perfectly to zero. The pollen grain's jitter is not noise in the measurement. It is the direct signature of the molecular storm that surrounds it, proving that even things that look still are being continuously agitated by things too small to see directly. The randomness of Brownian motion is not merely randomness in the informal sense of unpredictability, but randomness in the precise mathematical sense described by the theory of stochastic processes. The position of a Brownian particle as a function of time traces what mathematicians call a Wiener process, a path that is continuous but nowhere differentiable, meaning that at every moment the particle has a well-defined position but not a well-defined velocity, because the velocity would require taking a derivative that does not exist due to the fractal, jagged character of the trajectory. This mathematical structure, developed rigorously by Norbert Wiener in the 1920s, has applications far beyond the physics of colloidal particles. The same equations describe the diffusion of molecules in biological cells, the random walk of photons through stellar interiors and planetary atmospheres, the motion of charge carriers in semiconductors, and even the pricing dynamics of financial instruments in certain idealized models. The universality of the mathematics reflects the universality of the physical process. Whenever a small object is subject to many small, random, independent impulses, the resulting motion follows the Brownian statistics described by Einstein and Wiener. The biological significance of Brownian motion is enormous. Molecules in living cells are small enough to undergo significant Brownian motion, and this motion is not merely an obstacle to biological function but is frequently exploited by biological systems. Enzymes and other proteins find their substrates through Brownian diffusion, rather than directed movement. The transport of small molecules across cell membranes and through cytoplasm occurs partly through Brownian diffusion, rather than active transport. The conformational changes in proteins that underlie enzyme catalysis, signal transduction, and many other cellular processes are driven partly by the thermal energy available in the cellular environment. Life, at the molecular level, is not a triumph over Brownian motion but a sophisticated exploitation of it. The ground beneath your feet is moving relative to the ground beneath someone on another continent. The motion is slow by human perceptual standards, typically a few centimeters per year, but it is continuous, measurable with modern geodetic instruments, and has been proceeding for the entirety of Earth's geological history. The theory of plate tectonics, which describes this motion, was one of the major scientific revolutions of the 20th century and remains one of the most comprehensive and successful frameworks in the earth sciences. Earth's lithosphere, the rigid outer shell consisting of the crust and the uppermost mantle, is broken into a dozen or so major plates and several smaller ones. These plates move relative to each other at speeds ranging from less than a centimeter per year for the slowest plates to over 15 centimeters per year for the fastest. The plates are driven by convection in the mantle below, with a slow flow of hot mantle material driven by Earth's internal heat from radioactive decay and residual heat from formation, drags the overlying plates in patterns determined by the geometry of the convection cells. Where plates diverge, new oceanic crust is created at mid-ocean ridges. Magma wells up from the mantle, solidifies, and adds to the trailing edges of the separating plates. The mid-Atlantic ridge, running roughly north-south down the center of the Atlantic Ocean, is a divergent boundary where the North American plate moves westward and the Eurasian and African plates move eastward. The Atlantic Ocean is growing at a rate of roughly 2 to 4 centimeters per year, which means that over the roughly 200 million years since the Atlantic began to open, it has widened from a shallow rift valley to an ocean averaging roughly 3,000 kilometers wide. Where plates converge, one plate typically slides beneath the other in a process called subduction. The descending plate sinks into the mantle, where it is heated and eventually recycled. The Mariana Trench, the deepest point in the ocean, is a subduction zone where the Pacific Plate dives beneath the Mariana Plate. The Himalaya mountain range is a different type of convergent boundary, where the Indian subcontinent is colliding with the Eurasian continent. The Indian Plate is still moving northward at roughly 4 to 5 centimeters per year, slowly pushing the Himalayas upward while the ranges are simultaneously being worn down by erosion. Global Positioning System satellites, whose signals are now monitored by a worldwide network of precisely calibrated receivers, measure tectonic plate motions with millimeter accuracy and confirm the rates and directions predicted by the plate tectonic framework. The GPS receiver mounted on stable bedrock in North America and monitored over years shows a steady westward drift of several centimeters per year relative to receivers in Europe. This motion is not a measurement artifact. It is the literal, physical movement of the North American continent relative to the Eurasian and African continents, driven by the same convective forces that built and rebuilt the continents across billions of years. The ground has never been still. It has been moving for as long as Earth has had a mantle, and it will continue to move as long as Earth's interior retains heat sufficient to drive convection. The driving mechanism for plate tectonics remains an area of active research. The traditional picture attributed plate motion primarily to the dragging force of the convecting mantle on the base of the plates, with a mantle flow pattern determining where plates converge and diverge. More recent analyses suggest that slab pull, a tendency of subducting oceanic lithosphere to pull the rest of the plate behind it due to its density advantage over the surrounding mantle, may be a more important driver than mantle drag in many cases. Ridge push, the force exerted by the elevated mid-ocean ridges pushing the plates outward due to gravity, is a third contribution. The relative importance of these mechanisms varies among different plates. The heat driving the convection comes from two sources: the residual heat from Earth's formation and the heat produced by the radioactive decay of potassium-40, uranium-235, uranium-238, and thorium-232 in Earth's interior. The radioactive contribution currently provides roughly half the total heat flux from Earth's interior. Over billions of years, the radioactive heat sources will decay, and the total heat output will decrease, slowing the convection and eventually shutting down plate tectonics. The timescale for this is estimated at roughly 5 to 10 billion years into the future, after which Earth will become a geologically quiet planet, no longer moving its surface around, more like Mars and Venus today. The current rate and pattern of plate motion is captured in detail by the network of continuously operating GPS reference stations that has been built up over the past 3 decades. This network, called the International GNSS Service, includes hundreds of stations on bedrock around the world whose positions are measured continuously with millimeter precision. Time series from these stations reveal not just the steady tectonic drift of continental plates, but also the transient motions associated with large earthquakes, the slow post-seismic deformation that follows earthquakes, as the crust adjusts over months to years, the seasonal variations in continental position caused by surface loading from snow, groundwater, and ocean mass redistribution, and the longer-term changes associated with post-glacial rebound, a continuing uplift of regions that were depressed by the weight of ice sheets during the last glacial maximum. The stars in the night sky appear fixed because they are extremely far away, and because their actual velocities, while large, produce angular changes too slow for any human to notice on a human timescale. Arcturus, for example, one of the brightest stars in the northern sky, is moving across the sky at a rate of about 2.3 arcseconds per year. To the naked eye, this is completely invisible. Even over a human lifetime, the motion would amount to roughly 100 arcseconds, less than 1/30th of a degree. But over thousands of years, the constellations change their shapes, and over tens of millions of years, the stellar neighborhood changes beyond recognition. The proper motion of stars, their angular motion across the sky as seen from the solar system, reflects their velocity relative to the sun projected onto the plane perpendicular to the line of sight. Stars also have radial velocities, motion toward or away from us, measured through the Doppler shift of their spectral lines. Combining proper motion with radial velocity and with an independent distance measurement gives the full three-dimensional velocity of a star relative to the sun. The velocities of nearby stars relative to the sun range from a few kilometers per second to over 100 kilometers per second for high-velocity stars. The local standard of rest, defined as the average velocity of stars in the solar neighborhood, represents the mean orbital velocity of the sun's galactic neighborhood, and individual stars' velocities relative to this standard reflect their individual orbital histories in the galactic potential. Stars that formed in the galactic disk and have had few gravitational encounters with other objects tend to have low velocities relative to the local standard, a few tens of kilometers per second at most. Stars that have been scattered by close encounters or that formed in other parts of the galaxy before migrating to the solar neighborhood can have much higher velocities. The Gaia space mission, launched by the European Space Agency in 2013 and operating through its extended mission, has measured the positions, distances, and proper motions of approximately 1.5 billion stars with unprecedented precision. Gaia's data have revealed that the Milky Way stellar disk is not as simple as previously thought. There are streams and substructures of stars with coherent velocities that betray the disk's assembly history through mergers and interactions with other galaxies. The disk also shows wave-like vertical oscillations, as if the galaxy were still ringing from a past interaction with smaller galaxy, possibly the Sagittarius dwarf galaxy, which has been disrupted by the Milky Way's tidal forces. The most rapidly moving stars are called hypervelocity stars, objects moving faster than the galactic escape velocity and therefore on trajectories that will eventually take them out of the Milky Way entirely. Hypervelocity stars are thought to originate from binary star systems that pass too close to the supermassive black hole at the galactic center. During the interaction, one star was swallowed while the other was ejected at enormous speed. Some hypervelocity stars are moving at over 700 kilometers per second, fast enough to escape the galaxy in tens of millions of years. The classification of stellar motions into different kinematic populations reflects the star formation history and dynamical evolution of the Milky Way. Stars that formed early in the galaxy's history, when it was still assembling through mergers and had a more chaotic dynamical state, tend to have larger velocity dispersions relative to the disk's ordered rotation. These form the thick disk and stellar halo populations. Stars that formed later in the relatively quiet, settled disk environment tend to have smaller velocity dispersions and more nearly circular orbits, forming the thin disk population. The kinematic properties of a star thus encode information about when and where it formed. The Gaia satellite's radial velocity spectrometer, which has measured the radial velocities of millions of stars in addition to their proper motions, has enabled the detection of multiple kinematic substructures in the Milky Way's disk and halo that betray specific merger events in the galaxy's past. The most significant is the Gaia sausage or Gaia Enceladus structure, a population of stars in the inner halo, with a distinctive elongated distribution in velocity space, interpreted as the remnant of a galaxy with mass comparable to the Large Magellanic Cloud that merged with the Milky Way roughly 8 to 10 billion years ago. The merger stars are on highly eccentric orbits, diving deep into the inner galaxy and back out to large distances, tracing the orbital memory of the merger. The future proper motions of stars have been calculated for the brightest ones using current proper motion data, allowing prediction of how the constellation patterns will change over coming tens of thousands of years. In approximately 150,000 years, the constellation Orion will be barely recognizable. Betelgeuse will have moved significantly, and the overall pattern will be distorted. In 1 million years, the current constellations will be entirely unrecognizable, replaced by different patterns produced by stars whose individual motions have carried them to new positions. The theory of special relativity does not merely reveal new facts about motion. It fundamentally undermines the concept of absolute rest, demonstrating that the question of whether something is moving or at rest cannot be answered without specifying the reference frame, and that no reference frame is physically privileged over any other. In Newtonian mechanics, it was assumed that there was an absolute space, a fixed cosmic background against which all motion could in principle be measured. Newton acknowledged that this absolute space was undetectable directly, but postulated its existence as a conceptual anchor for the definitions of absolute motion and absolute rest. The Michelson-Morley experiment's failure to detect the motion of Earth through the supposed luminiferous ether, the medium through which light was assumed to propagate as sound propagates through air, removed the only candidate for a physical realization of absolute space. Einstein's resolution was to abandon absolute space entirely. Special relativity's first postulate, the principle of relativity, states that the laws of physics are identical in all inertial reference frames. There is no experiment local to any inertial frame that can determine whether that frame is at rest or in uniform motion. The concept of absolute rest has no physical meaning because there is no experiment that could identify a rest state. This does not mean that all motions are equivalent in all respects. Acceleration is detectable locally. An accelerating observer feels a force, while an inertial observer does not. General relativity extends this to include the equivalence between gravitational acceleration and kinematic acceleration. But uniform motion, constant velocity in a straight line, is truly undetectable without reference to external objects. A person on a smoothly moving train with opaque windows has no physical means of knowing how fast the train is moving, or even whether it is moving at all. The cosmic microwave background provides a reference frame that cosmologists use as an approximation to the cosmological rest frame. An observer at rest relative to the CMB sees it as isotropic, equally bright in all directions. An observer moving relative to the CMB sees it slightly blue-shifted in the direction of motion and slightly red-shifted opposite. The solar system's velocity relative to the CMB is measured at about 369 kilometers per second. But this CMB frame is not a physically privileged rest frame in the sense that Newton meant. It is simply the frame in which a specific physical entity, the thermal relic radiation, is isotropic. It is physically convenient but not ontologically special. General relativity goes further in dissolving the idea of rest. In curved spacetime, there is no global inertial frame, only local ones. The concept of rest at one location cannot be connected to the concept of rest at a distant location without path-dependent parallel transport of vectors, which means that even defining what it means for distant objects to be relatively at rest becomes ambiguous in the presence of significant curvature. The notion of rest that works reasonably well in the flat, weak gravity domain of everyday experience becomes increasingly problematic in the strongly curved spacetime near massive objects or on cosmological scales. The philosophical consequences of the relativity of motion extend beyond physics into questions about the nature of time and simultaneity that have occupied philosophers of science since special relativity was published. The philosopher of physics Harvey Brown has argued that the operational basis of special relativity, the way it connects to physical measurements made by real observers with real clocks and rulers, requires careful attention to what the relativity of motion actually implies about the structure of physical reality. The question of whether there is some deeper, preferred reference frame that special relativity merely prevents us from detecting, or whether the relativity of motion goes all the way down with no preferred frame, even at an ontological level, remains a matter of philosophical debate. Einstein himself was inconsistent on this question at different points in his life. He developed general relativity partly from an idea called Mach's principle, which holds that the inertia of any object is determined by the distribution of all other matter in the universe, and that there is no absolute space relative to which rotation is defined. General relativity does incorporate some of this idea through the phenomenon of frame dragging, in which rotating massive bodies drag the spacetime around them, but it does not fully implement Mach's principle in its Einstein 1915 form. The discovery of the cosmic microwave background and the measurement of the solar system's motion relative to it has given physicists a pragmatic rest frame for cosmological purposes. The CMB frame is the frame in which the radiation from the Big Bang appears isotropic, and it serves as a useful cosmological reference. But this frame has no special significance in fundamental physics. The laws of physics are the same in all inertial frames, and the CMB's isotropy in a particular frame reflects the initial conditions of the Big Bang rather than any absolute property of space. Rest remains a relative concept. Gravitational waves are ripples in the fabric of spacetime itself, produced when massive objects accelerate and propagating outward from their source at the speed of light. Their existence was predicted by Einstein in 1916 as a consequence of general relativity, and their direct detection in 2015 by the LIGO collaboration opened a new era in observational astronomy. Gravitational waves represent a form of motion so fundamental that it is motion of the geometry of spacetime rather than motion of anything within spacetime. When two black holes orbit each other in a binary system, losing energy to gravitational wave emission and spiraling closer, the spacetime around them is not static. It is dynamic, rippling with the waves produced by the orbital motion. These ripples travel outward at sea, carrying energy away from the system. The binary loses energy, and the orbital separation decreases, causing the orbital frequency to increase, which in turn causes the gravitational wave frequency and amplitude to increase in what is called a chirp signal. The entire spiral, from orbital separations of hundreds of kilometers to merger in milliseconds, is recorded in the gravitational wave signal. The first detected gravitational wave event, GW 150914, was produced by the merger of two black holes with masses of approximately 29 and 36 times the mass of the Sun, occurring about 1.3 billion light-years away. The gravitational waves that arrive at Earth on September 14, 2015, were produced approximately 1.3 billion years earlier, before complex life had fully established its dominance on Earth, and they had been traveling through the universe at the speed of light since the moment of their emission. The LIGO detectors that measure GW 150914 are 4-kilometer-long tunnels in L-shaped configurations, with laser interferometers that measure the distance between mirrors at each end with a precision of about 1,000th the diameter of a proton. When a gravitational wave passes, it stretches spacetime in one direction while compressing it in the perpendicular direction, and the detector registers this as a tiny difference in the lengths of its two arms. The amplitude of the gravitational wave strain measured from GW 150914 at the moment of peak signal was about 10 to the minus 21, meaning spacetime was stretched by about 1 part in a billion trillion, a distance ratio smaller than the ratio of an atomic nucleus to the distance from Earth to the Sun. Gravitational waves reveal that spacetime itself is not passive or static. It carries energy, propagates disturbances, and responds dynamically to the motions of the masses it contains. The merger of two black holes is one of the most violent events in the universe, releasing more power in gravitational waves during the final moments than all the stars in the observable universe emit in light combined. This power is not released into anything external to spacetime but is carried by the ripples of spacetime itself, propagating through the universe, affecting the geometry of every point they pass through, telling the universe about a collision that happened over 1 billion years ago in a galaxy far away. The population of gravitational wave sources detected since 2015 has grown substantially with each observing run by the LIGO and Virgo detectors, and the addition of the Kagra detector in Japan and the planned addition of LIGO India has expanded the network. By the end of LIGO's third observing run in 2020, the catalog contained roughly 90 candidate events, including binary black hole mergers, binary neutron star mergers, and possible neutron star black hole mergers. The properties of the detected binary black holes show a range of masses from roughly 5 to over 100 solar masses, with some events involving objects in the previously unknown mass gap between neutron stars and stellar mass black holes. The continuous gravitational wave sources represent another class of motion inscribed in spacetime. Unlike the brief chirp signals from binary mergers, continuous gravitational waves would be emitted by rotating neutron stars with non-spherical mass distributions, mountains on the neutron star surface, or by other configurations that produce a steady-state asymmetric rotation. No continuous gravitational wave has been detected yet, but the sensitivity of current detectors is sufficient to constrain the ellipticity of nearby pulsars to very small values, consistent with theoretically expected smooth surfaces. The detection of continuous gravitational waves will provide a new way to study the internal structure of neutron stars. The future of gravitational wave astronomy includes space-based detectors that will access a different frequency range from ground-based detectors. LISA, the Laser Interferometer Space Antenna being developed by the European Space Agency with expected launch in 2034, will consist of 3 spacecraft in a triangular formation 5 million kilometers on a side, connected by laser interferometers. LISA will detect gravitational waves from sources inaccessible to ground-based detectors, including supermassive black hole binary mergers at cosmological distances, the inspiral of stellar mass black holes into supermassive black holes in galactic centers, and perhaps cosmological backgrounds of gravitational waves from phase transitions in the early universe. If stillness is impossible at every scale of the present universe, the question naturally arises whether there was ever a moment when the universe was still before the motion began. The answer, insofar as current physics can address the question, is that motion was not something that began at some point in a previously static universe. Motion and the universe are coeval. Motion was present from the very beginning, and the beginning itself is most accurately described as a moment of extreme motion rather than a moment of stillness that then began to move. The Big Bang, the state of extreme density and temperature from which the observable universe evolved, is estimated to have occurred approximately 13.8 billion years ago, based on measurements of the expansion rate and the age of the oldest stars. At the earliest moments accessible to current physical theory, the Planck epoch lasting from time 0 to about 10 to the minus 43 seconds, the temperature and density were so extreme that our current physical theories break down. General relativity and quantum mechanics, the 2 most successful theories in physics, are individually adequate to describe their respective domains but have not been successfully unified, and the Planck epoch is a regime where both would need to apply simultaneously. What we do know is that as early as any physics we can currently describe, the universe was expanding rapidly, its matter was in ferocious thermal motion, and quantum fluctuations were playing an active and cosmologically significant role. The inflationary epoch, from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds, during which space expanded exponentially by at least a factor of 10 to the 26, produced the density fluctuations that seeded all subsequent structure formation. Those fluctuations were quantum in origin, the microscopic quantum uncertainty in the inflaton field, the hypothetical field driving inflation, was stretched to macroscopic scales by the rapid expansion and became the seeds of galaxies, galaxy clusters, and the cosmic web. After inflation, the universe was filled with hot, dense plasma of quarks, gluons, electrons, photons, and other fundamental particles, all in ferocious thermal motion, interacting and colliding at energies that no particle accelerator has come close to reproducing. As the universe expanded and cooled, the quarks and gluons combined into protons and neutrons, and then the protons and neutrons combined into the nuclei of the lightest elements, hydrogen, helium, and lithium, in the first few minutes. Big Bang nucleosynthesis. All of these processes depended entirely on the thermal motion of the particles involved. The motion that permeates the universe today is the direct descendant of the motion that was present at the Big Bang. Angular momentum, thermal energy, and the impulse from the initial expansion were all present in the beginning, and have been conserved and transformed ever since. The universe did not become a place of motion. The universe was born as motion. The specific question of what set the matter in motion at the Big Bang, what gave the universe its initial thermal energy and expansion velocity, remains connected to the problem of the Big Bang's own origin. In most inflationary cosmology frameworks, the hot dense state that we call the Big Bang was the end of the inflationary period, when the energy stored in the inflaton field that drove inflation was converted to thermal energy in the hot radiation-dominated universe through a process called reheating. The temperature reached at the end of reheating, the reheat temperature, depends on the specific inflationary model and is typically estimated at somewhere between 10 to the 9th and 10 to the 15 Kelvin. The thermal motion that permeated the universe at the end of inflation was not motion that was added to a previously still universe. It was the conversion of one form of energy, the potential energy of the inflaton field, into another form, the kinetic energy of thermal motion of the fundamental particles. The inflaton field's energy was itself a form of motion, the coherent oscillation of a quantum field. Before inflation, in the earliest moments that current physics can describe at all, the universe was governed by quantum gravity effects that we do not have a satisfactory theory to describe. Whether the universe had a beginning in any absolute sense, whether the Big Bang was the first moment of time, or whether it was a transition from some prior state, remains an open question in cosmology and physics. Some models, including certain versions of loop quantum cosmology, propose a minimum-size universe that reached its minimum at the Big Bang and had been contracting before that. In such models, the current expansion is the continuation of a prior era of motion in the opposite direction. In eternal inflation models, the Big Bang that produced our observable universe is one of infinitely many such events in a larger meta-universe where inflation is always occurring somewhere. In all of these frameworks, there is no moment of original stillness from which motion emerged. Motion is always present. The investigation of why nothing is ever still is, at its core, an investigation into the nature of physical reality at its most fundamental. The conclusion that stillness is not a possible physical state at any scale or by any physical process is one of those results that sounds paradoxical at first and then, once the reasoning is followed carefully, begins to seem not just true but necessary. A universe in which things could genuinely stop would be a different kind of universe from the one described by the laws of quantum mechanics, thermodynamics, and relativity. Our universe does not permit it. The different levels at which stillness is impossible are not independent discoveries bolted together. They reflect a deep coherence in the physical laws. Quantum mechanics forbids stillness at the subatomic level through the uncertainty principle. Thermodynamics forbids it at the material level through the absolute unattainability of zero temperature. General relativity and the expanding universe forbid it at the cosmic level. The conservation of angular momentum forbids it at the astrophysical level. The constancy of the speed of light makes the question of stillness for photons incoherent. The vacuum fluctuations make it impossible, even in the emptiness between things. What these layers of motion have in common is that they all reflect the same underlying reality. The universe is a system that began in extreme motion and whose laws conserve the total energy and momentum of that motion in perpetuity. The motions we see at every scale are not disturbances of an underlying stillness. They are the direct inheritance of the original motion, transformed in form and distributed differently, but never created, never destroyed, never allowed to fall to zero. The practical experience of stillness, which everyone has and which is psychologically important and genuinely meaningful, is not an illusion in a dismissive sense. It is real as an experience. What is illusory is the interpretation of that experience as evidence of an actual physical state of zero motion. The stillness you feel when sitting quietly in a room is an experience produced by a system of sensors calibrated to detect differences rather than absolutes, by the smoothness and consistency of the motions carrying you through the universe, and by the scale separation between the microscopic thermal and quantum motions and the macroscopic bodies your senses attend to. Once you understand this, the universe looks different. The stone on the table becomes a cloud of vibrating atoms riding a moving planet orbiting a moving star through a moving galaxy in an expanding universe. The empty space between objects becomes a sea of quantum vacuum fluctuations, virtual particles, and propagating gravitational waves from ancient cosmic collisions. The night sky becomes not a static backdrop but a collection of objects, each with a specific velocity and a specific destination, moving relative to each other and relative to the expanding spacetime they inhabit. Motion is not what happens to things that are otherwise still. Motion is what things are. The universe is not a place where motion occurs. The universe is motion, organized by the laws of physics into the patterns we call matter, energy, and space, and perpetuated by those same laws and forms that have never paused since the moment of their beginning. There is something initially disconcerting and ultimately exhilarating about the realization that not one atom of the universe has ever been still. The universe presents itself to everyday human experience as a mix of things that move and things that stay put. Trees are still. Mountains are still. The foundation of the building you are in is still. The precision with which this experience maps onto reality is remarkable. Within the window of human perception, for practical purposes, these things really are still in the sense that they are not moving relative to each other on any timescale that human activity concerns itself with. The abstraction of stillness is useful, and it is not wrong to use it. What it is not is physically real. At every scale below human perception, and at every scale above it, the universe is in continuous, irreducible motion. The stillness the human experience presents is a specific slice through a hierarchy of motions, a slice chosen by the bandwidth of human senses and the timescales of human concerns. This slice is real and valid for what it is, but it does not describe the full physical reality. Understanding the full hierarchy of motions that underlies apparent stillness is one of those shifts in perspective that permanently changes the way you see the world without making any practical difference to how you live in it. You still sit down, and sitting down still feels like rest. But behind that rest are quantum mechanical vibrations in every atom of the chair, thermal agitation in every molecule of your body, the planet beneath you rotating and orbiting and journeying through the galaxy being drawn toward 1 billion suns worth of mass on the other side of the local universe, and the universe itself expanding and cooling from the moment of its hot violent, an absolutely unmistakably moving beginning. Nothing is ever still. The universe has never allowed it and never will.